Acid-base equilibrium. In this lesson, we will be talking about the three theories of acids and bases. We will see examples of Arrhenius theory, Bronsted-Lowry theory, and Lewis acid-base theory. We will discuss the equilibrium constant Ka and how to distinguish between strong acids and weak acids. And then we will do some problems on pH. The three theories that we will be discussing today are Arrhenius theory, Bronsted-Lowry theory, Lewis acid-base theory. Before we proceed in this lesson, one of the things that we should bear in mind is when we study about acids and bases, we are actually studying the behavior of water when chemical substances are dissolved in them. Arrhenius theory. This is the first theory that we are going to discuss. By definition, an acid is any substance that increases the hydronium or hydrogen ion concentration in neutral water. And a base is any substance that increases the hydroxide ion concentration in neutral water. Examples of Arrhenius acids: hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid, carbonic acid. Sodium hydroxide, it's a base. Potassium hydroxide, it's a base. Calcium hydroxide and barium hydroxide followed by ammonium hydroxide. Sodium hydroxide is also called caustic soda, and potassium hydroxide is called caustic potash. Calcium hydroxide is commonly referred to as lime water. You can write an acid dissociation using this general expression where Ha represents an acid. H positive is the hydronium ion that it forms there, and A minus is a negative or anion that's formed during the dissociation of an acid. Common anions are nitrates, chlorides, acetates, chlorates, etc. We will see more examples as we go along. Dissociation constant Ka. This is an equilibrium constant expression based on the equation for the dissociation of an acid in water. And in this case, Ka is equals to H positive into A minus divided by Ha. The numerical value of Ka tells us the extent of ionization or dissociation. The larger the value of Ka, the stronger the acid. Smaller the value of Ka, we have a weak acid. So that's how we distinguish between a strong acid and a weak acid. Here are some examples of strong acids. There are 6 of them I have included here: perchloric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, and nitric acid. Since this list is shorter than the list for a weak acid, I would suggest that you memorize all these examples, because when we come to hydrolysis of salts, we need to recall strong acids. Examples of weak acids. I have also provided the Ka values, and you will notice that the Ka values are pretty small for these acids. I'm just going to run through these examples here: sulfurous acid, hydrogen sulfate, phosphoric acid, citric acid, nitrous acid, hydrofluoric acid, formic acid, acetic acid, carbonic acid, hydrogen cyanide, ammonium ions, and bicarbonate ions. Examples of Arrhenius bases: sodium hydroxide, ammonium hydroxide, calcium hydroxide. All of these substances, when dissolved in water, increases the hydroxide ions, therefore the solution is basic. Ion product of water, Kw. The value is 10 to the power of negative 14, and you need to memorize it. Ion product of water is actually the dissociation of water, or we can call it autoionization, and this is the equation that represents it. We can also write it like this. And now if you write an equilibrium constant expression, the subscript will be W, meaning it's ion product of water. So Kw is equals to H positive into OH minus ions. The value at 25 degrees Celsius is 10 to the power of negative 14. We can calculate the concentration of hydrogen ions in water. Again, we will look at the dissociation of water. Look at the change in concentration, minus x, x, and x. So which means if you write the equilibrium constant expression, Kw, which is 10 to the power of negative 14, we can replace it with the values of hydrogen ions and hydroxide ions. Since hydrogen ion is equals to x and hydroxide ion is equals to x, we can write it as Kw is equals to x squared. So if you solve for x, you get the value of the molar concentration of hydrogen ions and hydroxide ions. X is equals to root of Kw, or is equals to root of 10 to the power of negative 14, which is equals to 10 to the power of negative 7 moles per liter. That's the molarity of water, or pure water or distilled water, which has a pH of 7. pH and pOH. We have already calculated the hydrogen ion concentration and found it to be 10 to the power of negative 7 moles per liter. Therefore, pH is 7 using the Sorensen's equation for pH. pH is equal to negative log H positive ion. Similarly, we can calculate what we call the pOH because we have the hydroxide ion concentration, and that again is negative log OH minus, and we're going to replace it with 10 to the power of negative 7, which is equals to 7. So pH plus pOH is equals to 14. pOH is equals to 14 minus pH, and pH is 14 minus pOH. We can use these three equations conveniently when we have to determine the concentration, when we have to determine the pH or pOH based on the data that is given to us. The pH scale, if you look at the pH scale, it starts at 0, goes to 7, all the way up to 14. 7 is neutral, 14 is basic, and 0 is acidic. So if the pH of a solution is less than 7, the substance is supposed to be acidic, and if the pH is greater than 7, it's going to be basic. Here is a problem on pH. What is the pH of 500 milliliters of 0.005 mole or HCl? So HCl will undergo ionization. So let's look at HCl. What will happen to it? It will dissociate to give you H positive plus Cl minus. So if you know the concentration of HCl and the coefficient is 1 here and the coefficient is 1 here for hydrogen, therefore it will be exactly the same. So 0.005, 0.005, 0.005. We have the molar concentration of hydrogen ions, which is 0.005, and therefore in the equation pH is equals to negative log H positive. We are going to substitute this number and we get this equation, and the value of pH is found to be 2.3. Now in case you want to find out the pOH of the solution, all you have to do is use this equation. pOH is equals to 14 minus pH, which is 11.7. Here is a second problem, very similar. The only difference is instead of using hydrochloric acid, I've used sulfuric acid. You may want to see how the molecule undergoes dissociation. H2SO4 undergoes dissociation to form 2H positive plus SO4 2 negative. So when you take 1 mole of sulfuric acid, it gives you 2 moles of protons. And in order to determine the pH, we need the hydrogen ion concentration. that is twice the value. If we start with x moles of sulfuric acid dissociating, it gives you 2x moles of hydrogen ions. So the concentration of hydrogen ions has to be doubled. So pH is equals to negative log 2x. pH is equals to negative log 2 times 5 into 10 to the power of negative 3. And the pH will be 2.0. Or we can also find out the pOH. 14 minus 2 is 12. So pH for HCl in the previous problem was 2.3. pH for H2SO4 is 2.0. Interestingly, the molar concentrations of both the acids are the same, but the pH values are different, and sulfuric acid shows a higher hydrogen ion concentration because the molecules are dissociated and produces almost twice the number of hydrogen ions. The third question is, find the pH of a basic solution. So here you're given 0.001 mole per liter of sodium hydroxide. So when you dissolve sodium hydroxide in water, it changes into Na positive plus OH minus. So in this case, we are asking you the pH of a solution, but we are not giving you the hydrogen ion concentration. Instead, we are giving you the OH minus ion concentration. So how do you determine the pH? The best way is to determine the pOH and then convert it to pH. pOH, as we already know, is negative log OH minus, and we have the molar concentration, and that number goes in here. So pOH is equals to negative log 0.001, or pOH is equals to 3, and pH is equals to 14 minus pOH. That gives you 11. Mind you, this is a basic solution. A basic solution always has pH greater than 7, and the value that you have here is 11, which is greater than 7. Therefore, the calculation is right. The last problem here. Again, the same concentration for the base, 0.001, with the difference is calcium hydroxide, and we make an assumption that calcium hydroxide undergoes 100% dissociation, which means CaOH twice undergoes dissociation to give you Ca2 positive plus 2 OH minus. Therefore, the concentration of hydroxide ions doubles here. Again, since the hydrogen ion concentration is not given, we are going to find out the pOH and then find out the pH. So in this equation, we have to substitute the value of OH minus ions, and since this is doubling, the value that goes in is 2 times 0.001, which will give you a pOH of 2.69. And finally, the pH will be 14 minus pOH. That's going to be 11.31. So for the same concentration, if calcium hydroxide is completely dissociated, the concentration of calcium hydroxide will give a higher pH than that of sodium hydroxide because of dissociation. The next theory that we are going to discuss is the Bronsted-Lowry theory for acids and bases. Definitions: an acid is a proton donor, and all Arrhenius acids are Bronsted-Lowry acids too. A base is a proton acceptor. An amphoteric substance, this is a word that you may want to recall, is one that can act both as an acid and a base. You would be expected to identify amphoteric ions, species, or molecules in a dissociation, and these definitions will come in handy because it will show both the properties of an acid and a base. Some examples are water, bicarbonate, etc. We will see more examples in the following slides. Bronsted Lowry acid base illustration. The reaction between NH3H2O will give you NH4 positive and OH minus ions that are formed in water. So in this case, ammonia has got one more proton on the product side, which means it accepted a proton. Water on the other hand, lost a proton. Therefore, it donated a proton. So water is a donor and ammonia is an acceptor. Therefore, ammonia is a base, water is an acid. The products that are formed from the base will be the conjugate acid, and from the acid will be the conjugate base. The base and the conjugate acid differs by a proton. The acid and the conjugate base again differs by a proton. Second example, HCl plus H2O giving you H3O and Cl minus. In this case, HCl has lost a proton and H2O has gained a proton. Therefore, we can say HCl is an acid and water gained, therefore it's an accepting a proton, therefore it's a base. So HCl is the acid, water is the base. HCl and Cl minus is a pair. Similarly, the base and the conjugate acid would be H2O and H3O plus. Now, what's interesting in this case, if you look at water in the first equation and water in the second equation, in the first equation it's an acid, in the second equation it's a base. Therefore, water behaves like an amphoteric substance. In one case it behaved like an acid, in the second case it behaved like a base, or any substances that are capable of behaving like acids and bases are referred to as amphoteric substances. Polyprotic acids. An acid that have more than one proton is called a polyprotic acids. Here are a few examples: sulfuric acid, carbonic acid, and phosphoric acid. This is a diprotic acid. This again is a diprotic acid. This one is tri. If you have acids like HCl, HNO3, they are called monoprotic acids. H2O plus H2SO4 gives you H3O plus and HSO4 minus. H2O is the base, H2SO4 is the acid, the conjugate acid is H3O positive, and the conjugate base is HSO4 negative. So acid and conjugate base, base and conjugate acid, that is a pair. Now this molecule or this ion, HSO4 minus, can become a reactant again and react with water and give you H3O plus and SO4 negative. So in this case, HSO4 has lost a proton, therefore this is an acid. H2O has gained the proton and therefore it's a base. So these two is a pair, HSO4 and sulfate, acid and the conjugate base, and similarly this is the base and the conjugate acid. What's interesting here is HSO4 in the first equation is a conjugate base. In the second equation, HSO4 is an acid. Therefore, we have again another ionic species that is behaving like a base and an acid. Hence, it's amphoteric in nature. Same equation. Here we are writing an equilibrium constant expression because we are showing the dissociation of the acid one proton at a time. Therefore, this constant is called Ka1. So if you take this reactant and write the second equation, the dissociation constant will look like this for the second stage, and then the dissociation constant is called Ka2. Ka1 is much larger than Ka2. Here are a few cases of compounds that are illustrated here. You have to identify which of them is amphoteric and which of them is not. This is an amphoteric substance. This is an amphoteric substance. This is not an amphoteric substance. This is an amphoteric substance. This is not. This is no, no. So we will write the two possibilities here. This can lose a proton and change into OH minus, or gain a proton and change into H3O plus. This can lose a proton and change into SO4 2 negative, and this can gain a proton and change into, again, this can lose a proton and change into PO4 3 negative, and this could gain and change into H2PO4 negative. This one again can lose a proton and change into HPO4 2 negative, and it could gain a proton and change into H3PO4. This can lose a proton, but it cannot gain a proton, therefore it's not amphoteric. H3O positive can lose a proton but cannot gain a second proton. This does not have a proton, therefore it cannot lose and show acidic property. That's how you distinguish between ionic compounds that can behave like an acid and a base, or an amphoteric substance, and a substance that does not show that property. Lewis acid base theory. This is the third theory that we're going to look at. An electron deficient species is a Lewis acid. An electron deficient species means a molecule, atom, or ion that has an empty orbital. Therefore, it can accommodate a pair of electrons. Some examples are H positive, BF3 negative, or BF3, and AlCl3. Lewis bases. An electron-rich species is a Lewis base, which means a molecule, atom, or an ion that has a lone pair which it is capable of donating to any electron deficient species. Some examples are ammonia, water, chloride ions. We will see more as we go along. Here is an illustration for the interaction, Lewis acid base interaction. If you look at ammonia, ammonia can interact with a proton to form ammonium ion. So NH3 plus H positive. So the lone pair from nitrogen is donated into hydrogen's 1s orbital to form NH4 positive. So it looks like this. The next example would be formation of hydronium ion. The product formed is similar to ammonia. So a pair of electrons is donated to the hydrogen ion, therefore it will. So this is how the hydronium ion looks like, and both the electrons are coming from a single atom, therefore it's a coordinate covalent bond. So it is also an illustration of Lewis acid base interaction. That was a very brief introduction into acid base theories.